Hello and welcome to another video. In this video we're going to be working on eliminate maximum number of monsters. And in this problem you're playing a video game where you're defending a city from a group of n monsters. You're given a zero indexed array of distances and speeds, and so the distance is the starting distance for a monster away from the city, and the speed is the speed of the monster, and they walk towards it at their speed all the time. And so you have a weapon that can shoot one monster, and once it shoots, it takes 1 minute to charge, and the weapon is fully charged in the beginning. You lose when a monster reaches a city, and if a monster reaches a city right when your weapon is ready to fire, that's considered a loss. And you want to return how many monsters can you kill before a monster reaches the city. So that can be all of them, that can be none of them, and so on. Obviously, it's never going to be none of them because your weapon's ready right away. But let's kind of go over these examples. So in the first one, you have 3 monsters that are 1, 3, 4 away at speeds 1, 1, 1. So your gun is ready at time 0, so you can kill this one. Then your gun is ready again at time 1, so you can kill this one. And then your gun is ready again at time 2. And so, like it says, you have enough time to eliminate all 3 because the first one takes 1 second, but you can kill it. The second one takes 3 seconds, but you can kill it. And the third one takes 4 seconds. So in the second example, you have 2 monsters that are both 1 away, and then 2 monsters that are 2 and 3 away. So here you can only kill 1, because once you kill this first one, then the second one reaches the city at time 1, and your gun just recharged. So you kill the first one, then you lose. So you can only kill 1. And in the third one, so let's take a look. The distances of monsters 3, 2, 4. You can eliminate the first monster, so you would kill this one right here. And then the second one reaches the city at time roughly like 1.5, and you have time to kill. Do you have time to kill? Let's take a look. Let's see. Distances, you went the first. After a minute, distances of the monsters are. All right. So after a minute. All right. So I misread that. So this one will take less than a second to reach the city, and this one will also take less than a second to reach the city because the distance is 2 and the speed is 3. So the time is distance over speed. So the time here would be like roughly 2 over 3, which would be like 2/3 of a second. So essentially, we can write this down. So the time it takes for a monster to reach the city is distance over speed. So for example, if you're at 4 traveling at speed 2, it would take you 2 seconds, right? So what we first want to do is we want to take our distances and speeds, and I'll kind of show you like a few ways to solve this problem, and this is going to be the easiest way. So we can take our distances and speeds and divide them to get all of the times for a monster to reach a city. So let's just say we have some random array. We have like 1, 2, 3, 4, 5, let's say, and they all have speeds like, just say like 5, 4, 3, 2, 1 or something. So essentially what we can do is we can get an array of times, and then we can sort that array, and then we'll kind of have like a way to know when the monsters will reach the city. And obviously you're just going to want to shoot the monsters by whichever one reaches the city first. That's the other thing. The problem's a little bit confusing. It's not like they're in a line. Like a monster in the back can reach the city first, so you might want to shoot that one first. So essentially, for an array like this, let's say these are the distances and these are the speeds. Let's calculate how long this takes for all of these, roughly. So for the times, so we have 1 over 5. So this one will roughly reach the city at 0.2. Then we have 2 over 4, so roughly at 0.5. Then we have 3 over 3, so roughly at 1. And we have 4 over 2, so roughly at 2, and 5 over 1, so roughly at 5. So these are the times. They happen to be sorted, but you're going to want to sort your times, right? So you get some times, you sort them, and then you just simply go through one by one, and you just figure out, like, when will my gun be ready? So your gun is ready at 0, so you can shoot this one, and then you just keep going through the rest of it, and anytime your gun's not ready, that means you lose, right? So your gun's ready here, so your result will be 1. Then the next time your gun is ready is you add 1, so it'll be ready at 1. But here you already have a monster at 0.5, so you lose right here. Let's say I didn't have these, for example. Let's say I didn't have these 2, I just had these 3 times. Then what it would look like is you would shoot this one at 0, right? And then your gun's ready at 1. Then you come here, and your gun's ready at 1, but the monster comes at 2, so you can shoot this one. Then your gun is ready at 2. And then this monster comes here, and so you are able to shoot this one, so you're able to shoot all 3, and your result will be 3. But essentially, the idea is just get times, sort them, then just go through times, and if gun is ready before the time, then result +1, otherwise fail and return result. And the gun, for the gun being ready, so whatever the state it was, so if the gun was ready at like 1, then, you know, if you shoot it, then the gun is ready at 1 + 1 and 2 + 1 and so on, right? So it takes 1 second to recharge, so you literally just go through all of them, and then if you can shoot it, update the gun to be ready at the next second, then keep checking, is the gun ready before the monster gets there, and the gun has to be ready before the monster gets there, and you just return the result. So pretty straightforward. That's one solution. Now, another very similar solution is instead of getting this times and sorting, you can actually get all of these times, and then you can heapify. So it's very similar, almost the same code. So get times, heapify, and then you just, instead of sorting, you just keep heap popping the minimum out of the times, and you keep checking, is my gun ready that way? And so sorting would be n log n, right? But heapify is still worst case n log n, but it might be a little bit better because you might break earlier. Where sorting, you're doing like all the work up front, and even if like you fail right away, you're still sorting the whole thing. But heapify, to do the actual heapify, would only be O of n, and then you might like only have to pop like 1 or 2 elements, so your actual practical worst case would be a lot better. So those are the two ways of sort or heapify that you can like very easily do this, where you just sort by the first monster each city, and you just check 1 by 1, do I have enough time to shoot this one? If I do, when will my gun be ready again? Do I have enough time to shoot the next one? And so on and so on and so on. So that's one way to do this problem. Now we are going to go through another way to do this problem that's actually better in theory, but actually has a worse runtime in LeetCode. So let's go through that. So the idea behind this problem is we're going to do a bucket sort. And basically, if you look at these constraints, the biggest number you can have for distance and speed is 10 to the 5th. And remember, time is distance over speed. So the biggest number we can have for time is 10 to the 5th, right? So distance would be 10 to the 5th, and speed would be 1. That's the biggest number we can have. And notice that's about the same as the length of the array, right? So the time it takes to go through every single possible time is about the same length as the length of the array. Now, if this was a lot smaller, then this would be a way better approach. Like if this was like 100, this would be a lot better. And if this was a lot bigger, like if this was 10 to the 9th, and this was really small, then this would be a lot worse. And I'll kind of explain the time complexity and why that is. But essentially, instead of sorting our times, what we're going to do is we're going to actually create a hash map of time and the number of monsters that arrive at that time. Now, this is a little tricky because you might think like, well, the time is distance over time. And the problem is these can be like all kinds of decimals, right? Like 1.89, 2.76. How do I actually, like, there's way too many times to check here, right? If I just check manually time by time. And so if you think about it, let's say the monster arrives at 1.89 and the gun is ready at some time. Well, because let's say the gun's ready at 2, for example. So if the gun's ready at 2, the monster would get there first, right? What if the gun was ready at 1? Then the gun would be ready. And if the gun was ready at 3, then this would be, then the gun would be too late. So no matter what, we can actually take our time and round it up to the nearest whole number. And then we can kind of do the same thing where if it's a tie between the gun and the monster, then you lose. And that basically, so let's say the gun's ready at 2. That means that anything 1.01 to 2 is the same thing, right? 1.01 to 2 means the gun's not ready in time. So any number, you can just round up to the nearest whole number, and it's basically the same comparison. So we're going to get our times, we are going to round them up, and then for every single time, we are going to check how many monsters arrive at that time. So now that we have all our times, we can go through this whole array, get a dictionary of time and number of monsters. So let's kind of walk through maybe an example of doing that. So let's say we have some times and kind of like what we're going to do. So let's say we have some array. So we'll just take some random numbers, 2, 4, 1, 5, 8, with some speeds of like, say 1, 2, 1, 2, 1 maybe. Okay, so let's get our times. And then what we're going to do is we're going to actually, remember, we're going to round all these times up, and then we're going to store the count of monsters that arrive at that time. So in our times dictionary, let's take a look. So for our first time, it will be at time 2, right? Distance over speed. So at time 2, there is one element. So that's this one right here. At the second time, what's the time here? So the time is 2 again. So now we have another element. So we have 2. Then we have 1 over 1, which is at time 1. So at 1, there's one element. This one right here. 5 over 2, which is 2.5, but we round up. So 3, there's one element. And then finally at 8, there's one element. So essentially, this will tell you, like, these are all my arrival times. And I just want to keep track of, like, while I do this, I just want to keep track of, like, what's the maximal time I got. So I know that I got 8. So I can just loop from 1 to 8. You can maybe even keep track of a min time if you want to. It doesn't really affect it that much. So if you want, maybe that's like a slight optimization. But essentially, keep track of the maximum time, and you're just going to say, okay, I'm going to loop through all of my times now, manually, 1 through 8. I don't know which ones are in the dictionary because I didn't sort anything. But I'm literally just going to loop through all my times, and then depending on the number of monsters, I'm just going to see how many times I have to fire my gun and what my result is. So the gun is available at 0, and the result is 0. So let's kind of walk through what's going to happen here. So essentially, we're going to check for time equals, we're going to loop from time equals 1 to 8, and we're going to say, okay, well, for the gun at 1, is there a monster, and how many are there? Yes, there's 1. So that means for the number of monsters, like let's say at 1 there were 2 monsters, for example. Then we'd have to loop this many times and see if we can kill them all, or how many we can kill. But in this case, there's 1, but let's say there were 2. So we'd have to loop 2 times. So we'd say, like, okay, well, the first monster, like, we'd have to see, like, how many, we'd have to reload our gun and see how many we can kill that arrive at time 1. So we'd say, like, okay, well, we can kill the first one for sure. So this would be 1. And then my gun would be ready at 1. But now for the second one, it would also arrive at 1, and my gun's not ready, so I would just return. So essentially, for every single key, you just loop value amount of times, and you see, like, for your gun, how many can I kill? And if I can't kill all of them, then I just return right away. But luckily for us, there was only 1, so we could kill it. So we're going to kill it. Our gun is ready at 1. Our result is 1. Then we are going to check at time 2. Is there anything? And there is something at time 2. There are 2 monsters. So let's see how many we can kill there. So we're going to loop twice. So can we kill the first one? So our gun is ready at 1 time, and the monster arrives at 2, so we can kill that one. Now our gun will be recharged at time 2, and there's still 1 more monster at time 2. Can I kill that one? Well, our gun's ready at time 2, and the monster arrives at time 2, so I lose. Right? So I killed 2 total, and I return. So essentially, you are, let's write this down, loop from 1 to max time for each key that we find, or for each time that we find loop I times, where I is number of value, see how many we can kill by updating gun, right? So we're kind of like doing the updating gun kind of the same way, where we're just saying, like, okay, our gun is whatever it was, let's just keep updating gun, see how many we can kill, and then if we can't kill them all, return when we can't, otherwise go to next time, right? So we were basically manually looking through times and just checking if they are in our hash map. So we're not going through our keys, because we can't go through our keys, because in order for this to work, going through our keys, we'd have to sort our keys, and then we're sorting, so that's n log n. So we're not sorting, we're just manually going through, like, times 1 to max time, so we're guaranteed going through a sorted order, but just a lot of times might not be there, right? Like, let's say 1 wasn't here and 2 wasn't here. Let's say these keys weren't here. So you'd say, like, okay, I'm at 1, there's nothing here. Okay, let's go to 2, there's nothing here. Okay, I'm at 3, now there is a time. And then you just keep track of, like, when your gun was last fired and your result. And the idea is, yeah, so we just do this, and this is better because to get all our times, that's going to be O of n, where n is the length of the array. And then to go through our dictionary, so how many keys do we have? So we have O of m, where m is the biggest time. But if you look at these constraints, if we scroll up, the biggest time is, like I said, 10 to the 5th. And for each constraint, you have to loop through some numbers, but how many values are there total? So the number of values there are total is O of n. So it's O of m plus O of n would be the solution. And so if this was like 10 to the fifth times, or plus 10 to the fifth, that would be the runtime here, worst case. Where in the sorting solution, it would be log 10 to the fifth times 10 to the fifth. So I know this was kind of confusing, and like I said, if you don't like this one, you can just totally do this easy time sorted solution where you just get all the times, you sort the times, and you just go one by one, is my gun ready before that time? So that would be like the the easy medium solution. This one's a little bit trickier, but just like I said, especially if this number was way smaller than 10 to the fifth, let's say the biggest number was like 100 or 200, this would be way better, right? Because then m would only be 200. In this case, they're equal, so it's better, but not too much better. And then obviously, if this was like 10 to the 9th, then this would be a lot worse. So this depends highly on constraints. Which one's better, the bucket or the sorting this array here? But I just wanted to show you something new, kind of rarely used algorithm. So let's actually code this one up, because I'm not going to code up just the sort and going through the sorted times, because that one's like really straightforward. Okay. So we're going to get our times dictionary. And we're going to get a max time, and we can even get a min time if we want. So we'll say min time. Let's just say min time. Let's make it like infinity or something, right? Let's make it infinity. Our max time will make 0. And then we can sort from min time to max time. So we'll say gun ready is ready at 0. And then we're essentially going to loop through all of our distances, kind of like we would to get all the time. So we'd say for I in range length distance. Let's say the time is, like I said, we're going to ceiling it, because if something is ready at 1.8, if a monster arrives at 1.88, we can say it arrives at 2, and it would be the same. It would work out exactly the same way. So we'll say ceiling of, and this also ensures that our times, we don't have like a billion times, right? If you have a whole bunch of decimal times, you wouldn't be able to loop through them. So we're going to say distance over speed, ceiling, and then we're going to say if time in not in times. So if time's not in times, if this is a new one, then we'll say times time equals 0. And then regardless if it's in there or not, we will update by 1 now. So times time plus equals 1. And then here we'll say max time equals max of max time and we'll say min time equals min of min time and time. Okay, so now that we have our dictionary of times and how many monsters arrive in that time, now we're just going to manually loop from min time to max time until we either get all of the monsters or we break somewhere. So we don't know where the times are. We're just manually looping. We don't know where the keys are. We can't sort them because that would be slow. So we're going to say for I in range min time max time plus 1 if we do need to have a result. Yeah, so we're going to have a result equals 0. So we'll say if the result equals and let's actually make another variable of like d or something, equals length of distance. So if the result equals d, that means we've killed every monster, so we should just return. And then if the time is not, maybe we can call this like better name, so we'll say for time. Yeah, if time is not in times, that means it's not in our dictionary, so let's just go to the next time. So let's continue here. And now we have to check how many monsters are in that time, and for every single one, we have to see, can we fire the gun? If we can, we'll keep adding to the result. If not, we'll return straight away. So we'll say for, we don't need to use this, in range times time for however many monsters there are in here. If gun, so all these monsters are going to arrive at time, but we have to keep firing our gun and seeing, can we kill it, right? So if gun ready is greater than or equal to time, that means the gun's not ready in time. So then we would have to return however many monsters we killed. Otherwise, we will say gun ready plus equals 1, so we'll recharge it, and we will add 1 to the result. And finally, we can return the result here. So kind of to walk through this one more time. So essentially, max time and min time are going to have the you don't really need to have these two. Like if you wanted to, you can just loop from like 0 to 10 to the 5th. But if your numbers are like way smaller, this kind of saves some time. Essentially, they're just going to be the constraints of the times we're searching for. So every time we get a time, we will say, is it the min time or the max time? And this will make this loop run faster. And so our gun ready is ready at 0, and our result of monsters is 0. D is the length of the dictionary. So we get all of the times, and we add them to the times dictionary. So the times dictionary will have a time where a monster was killed and a count of all the monsters that were killed in that time. And then we are doing ceiling just to make sure that we can bucket them into times. Because if you have something like 1.66, 1.77, 1.88, and so on, you want to bucket all of those into a integer number. And then finally, we loop through all of our times from the min time to the max time. And we say, okay, if we've killed every single monster, let's return. If this time is not, if there are no monsters killed in that time, let's continue. Otherwise, for every single monster that was killed in that time, let's see if I can kill it, or if, sorry, not killed, but arrives at the time. For every monster that arrives at the time, can I kill it? If not, let's return the result because I failed. If yes, let's shoot, and then let's update our gun alongside to the result. So let's see if we have a solution. Looks like we do. And so yeah, I think this actually runs slower on LeetCode than the like sort easy solution, which is kind of funny. So yeah, it actually runs slower, but in theory, this is a better solution. So yeah, let's think about the time and space for this one. Maybe run it. I am curious also. Let's see if we just like get rid of these, if it runs faster. I am curious about that. So if I just hard code, like, I think the max time is like 10 to the 5th. So if I just say like 0, 10 to the 5th or something. And this, I have to get rid of this. Okay. Yeah, so either way, it's about, I'm going to leave it in here, but in theory, this should be faster. In practice, it's just about like the LeetCode tests. So I think when I did the sorted solution, yeah, I think this is like the sorted solution. It was like a little bit faster, but in theory, this has better time complexity. So it's just literally about the LeetCode test for it. So here we have O of n plus m, where n is the length of the array and m is the maximum time I can have. And then the space is O of, so it's just going to be O of n. It's actually going to be O of m here. So yeah, it's going to be O of m, where, yeah, this could be better. Like, once again, it all depends on what your time is and stuff. Actually, is it O of m? No, it's not O of m, because you will only store things that arrive at some time. So I think this is actually O of n still. Yeah, I think this is O of n, because for every single monster, you count its arrival time. But in practice, it's going to be smaller than this because you'll have a bunch of monsters that arrive in that time. So it'll be something like this. Yeah, and I think that's going to be all for this problem. So hopefully you liked it. And like I said, it runs slower on LeetCode, but in practice, it's a better, or in theory, it's a better solution. So hopefully you did like it. And if you did like it, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.